mention, and then I'll discuss some general question about this algebraic construction. So yeah, so this is a mix of things. So I'll start with biset category. So in the end, for me, this Mackey functors will be functors, additive functors from this category. And this category has objects, all finite groups. And morphisms here will be, so there will be several different conventions for left and right here, but this will be this. So this is the full double Burnside ring. So this is a Grothendieck group of group of finite isomorphism classes of finite Hg bisets. So here Hx on the left and Gx on the right, as is written, as it should be. Right, and then the composition is given by this. Did Radu introduce this tensor? Yeah, we did. So the composition is given by this sort of tensor product construction. So if X is a KH biset, and bracket denotes the isomorphism class, then this is this guy. So where this is X cross Y modulo the relation as you see in the tensor product of modules. And that's that has natural KG biset structure. So I'll describe this category a little bit more concretely, more with more detail. So this yep. Yeah, so H is on the left. So here X is yeah, KH H. Yeah. Yeah. So this is as additive group, just free abelian group on isomorphism classes of transitive G cross H sets, which are so G cross H over some subgroup L, and these L's up here, ones from each conjugacy classes. So you take this up to conjugacy, right? So what are these subgroups? These subgroups. So we need to know what these subgroups are. Subgroups of direct product of groups. So some, I mean, the Gursa actually, for some reason I don't know, thought about this problem and actually gave complete description of these subgroups. So for that we need a small terminology. Pair of groups is called a section of a group G if they are subgroups of G and one is a normal subgroup of the other. You can take the quotient and you'll get section quotient, but for some reason for some purposes, you want to distinguish cases where you have isomorphic quotients, but still you have different groups having those quotients. So this is a section. And then the set of subgroups of G cross H is in bijection with this quintuples, where the first pair is a section of left-hand side group. So this is a section of G, and this is section of H, and they have isomorphic quotients, and phi is one particular isomorphism going from right to left. I mean, it doesn't matter, but you can choose it to be that way. So this is abstract group isomorphism. Yeah. And the correspondence goes like this. If L is a subgroup of G cross H, then there are these projection maps, right? G cross H goes to G and H by these projection maps. Let's call them P1 and P2. Then this capital P1 is image of G under L, sorry, under P1, and K1 is image of L intersected with G cross 1. And this P2 and K2 are defined similarly. It turns out that they form sections of G and H, and they have isomorphic quotients, and isomorphism is given by sending H, the coset of H to coset of G whenever G comma H is an element of the group. Yeah. So that's bijection. Moreover, there is natural subgroup, inclusion partial order in this quintuple, which, well, another way of thinking of that is, so you have bijection, so you can transport the subgroup subgroup inclusion relation onto this side, and that will be very natural. That can be expressed very naturally in terms of these quintuples. And similarly, this set of subgroups of G cross H, of course, is acted by G cross H, and that action has very natural natural counterpart on this side, as you can imagine. I mean, this is isomorphism, so you conjugate on one side, conjugate on the other side, things like that. So so let me just write that this is in fact an isomorphism of natural G cross H posets. Okay. So that's it. So at least this group, as abelian group, is free abelian group, and the bases are given in bijection with G cross H conjugacy classes of these quintuples. Yeah. So that's one thing. So so later we'll just write this isomorphism class of this transitive G cross H set as just bracket of these quintuples, corresponding quintuples. And this goes from H to G, so let's write it this way. Right? And then what about the composition? Right? For that, we need first, before to describe this carefully, we need to have a operation on subgroups of these products of groups. So suppose L is a subgroup of G cross H, and M is a subgroup of H cross K. Then you have this relation product. So they can be viewed as relations between this set, between G and H. Yeah? So if the G and H were equal, this is really a subset of G cross itself. So it's a relation on G. And in a similar way, this is relation or correspondence. If they are different, sometimes this is called correspondence, subset of G cross H. But anyway, so they have natural relation correspondence product, which is simply given by taking those GKs having H in the middle, something in the middle. Yeah. So G cross H is in L, H cross K is in M. And if they are, so this can be defined for any subsets, but if they are subgroups, this is a subgroup of G cross K. And in terms of this quintuple representation, so if L is this quintuple, P1, K1 on one side, P2, K2 on the other side, and this is rectangle is an isomorphism. Yeah? Imagine that this is an isomorphism. So suppose this is P1, this is M, pictorially represented as P1, K1 dash, P2, K2 dash. Then their relation product, correspondence product, is something in between. This will be so this will be some subquotient of this bigger sections, where these subquotients, these sections, they are obtained by butterfly lemma. So whenever you have so these two groups are inside the middle group H, and whenever you have a group and two sections, then you have this butterfly lemma, which gives subsections, and these are precisely those sections coming up, arising in the butterfly lemma. Yeah. So okay, and then the product of cosets of L times cosets of, this composition is it's a double. It has double coset formula, and double coset is over in H, and you take this P2 subgroup of the left-hand side and P1 subgroup on the right-hand side. You take the coset representatives, double coset representatives here, and then you form G cross H, K, sorry. And here L correspondence composition with this conjugation. Yeah, so that's the product, the composition in this category. And this is a bit complicated, but you can easily check this. But the main thing here is this biset composition preserves section size, or section containment in general. Section quotient size, for example. And that seems to be the key property that is exploited over and over again in this game. Okay, so that's biset category. So we've heard that we only want to consider left-free or bi-free things. So they can be obtained as subcategories. So again, I'm going to define these functors as just covariant functors. So in that case, I think we need to define right-free subcategory. So objects are the same. And the home set is just the right-free double Burnside ring of H and G. So the action of the group G is free. So in terms of the that notation, this is simply Z span of quintuples, brackets of quintuples of this form. So right hand side is free, so that means you will have arbitrary thing on the left, but on the right the K group should be trivial. That's what it is. And then you put all possible things here. And you can easily show that this forms a subcategory. And then you have bi-free thing, where objects are the same, and here home set is bi-free double Burnside group, where both sides are free, and the quintuple notation, you have both K groups are trivial. And here you put all possible U and V and 1. And they should go from G to H. Yeah? So here also. Yeah. And so when F is a fusion system, you can define this subcategory in terms of fusion system, where objects are objects of the fusion system, and home set is a submodule of this subgroup of this Burnside group, where all these are bi-free. And moreover, the phi map, so here let's write down what these are more carefully here. So U should be the subgroup of Q, V should be subgroup of P, and they are isomorphic, and isomorphism is given by this phi. And this phi should be inside the category F. Yeah. So and the axioms of fusion systems implies that this forms a subcategory. It's almost like axioms of fusion systems are designed so that this is a subcategory. If you go through the check, yeah. Okay, then right. Yeah. I don't require saturation at this point. No, you don't need saturation here. Yeah. Covariant. I'll define it as covariant. Yeah. No. So either go from right to left. So you don't have deflation, but you have inflation. The second K group being 0 means there is no deflation. And now I define biset functor, or this is globally defined. In the literature, there are many different names, but this is one name, globally defined Mackey functor. Right. So you take your favorite subcategory of F, one of those, and a biset functor defined on D is an additive functor, covariant additive functor, covariant additive functor from D to the category of abelian groups. Yeah? So that's the definition. So that's algebraic definition, and many things fit into this framework. So, okay, I mean this is, so if this is C, this is some additive category. Well, no, is it additive? Pre-additive category here. And you are looking at functors, additive functors from there, then you can easily get this kind of functor using any representable functor. For example, let's pick just trivial group and keep this part blank. Then this representable functor is a biset functor. And well, in fact, but this means that right-hand action is trivial. So this is just the usual Burnside ring functor. This is a biset functor defined on the full biset category. So in representation theory of finite groups, you often consider this fix a field, and you consider, for finite group G, you consider this representation ring. Of G over F. This is a Grothendieck group of finitely generated FG modules, where the relation is given by short exact sequences. Yeah. So this is, if characteristic of F is 0, then taking representation ring gives a biset functor defined on the entire biset category. So you have all standard functors that you like: induction, restriction, inflation, deflation, everything. But in general, you only get biset functor on the right-free subcategory, precisely because for general F you don't get deflation as a well-defined map between these categories. This is because so the functor here will be defined as tensor products, and the tensor product corresponding to deflation is so here deflation from G to G mod n, where n is normal subgroup. It will be given by basically F G mod n tensor over Fg, and this is not exact in general. because this is not exact in general, yeah, so this cannot be defined at this level. So so you don't. Then that's fine. Yeah, sure. So this is but others are you have all induction restriction and inflations. So sometimes this is called inflation functor. And so when K is a field, this cohomology functor with constant coefficient K, this is an example of inflation functor. You have inflation, but you don't have deflation. Is also an inflation functor. Right. So, and by restriction, so I mean, yeah. So this is defined on CRF, but that contains CBF as subcategory, and that contains CF as a subcategory, where F is a fusion system. So by restriction, is a biset functor for CF, for any fusion system F, and this is, so I'll indicate how this works. This is exactly the same as the Mackey functor that Antonio defined. This is the same as Mackey functor. I'll describe the, I'll indicate at least the correspondence between them. So this cohomology functor with trivial coefficients can be viewed as Mackey functor for any fusion system this way. So one good thing of this point of view is that these biset functors for any D, it's just additive functor from this category, which is essentially small, and go into abelian category. So it's like module category. So you have this category itself is an abelian category, and where exactness is defined component-wise. So you have simple functors, projective functors, everything. And so, for example, when D is one of these categories, the simple biset functors, and let's take some arbitrary fixed base ring as some commutative ring. In practice, it'll be some field. But the simple biset functors on D over K, they are in bijection with pairs, where H is an object of the category, and V is simple module for K auto-automorphism group of H. And okay, so I mean up to isomorphism. Up to isomorphism. There is obvious notion of isomorphism as isomorphism of the groups, which transports the module structure. Yeah. So and this is where here we use that biset composition preserves the section quotient size. We denote the simple biset functor corresponding to this pair as S subscript. Yep. Out. Yeah. Out H, because for all these categories, out H, there is a map from out H to DHH. given by, yeah, right? So phi goes to, in the notation that I introduced, yeah, this is a well-defined map, yeah, actually inclusion.